So let me turn everything over to Per Ake.
Thanks. And maybe.
Yes, I'm actually going to start off. I'm Molly Weiss. Happy to see so many here tonight. I'm the CMO and partner at Speedment. And we are basically working with legacy systems with the efficiency and low latency for those. And with me today I have our CTO and daddy for the solution. It's Per Ake. And he's very active within different community centers. He's an alumni at Java 1. He's done different kind of things. He's also author of the Modern Java, given out by DZone. Please check it out. So I pass on to you, Per Ake. Maybe you could tell them why I'm here.
Thanks, Molly.
Yeah?
So the reason Molly is staying here is that I need to catch a flight back because tomorrow is my 50th birthday. And I'll let you know.
Happy birthday to you.
Thanks, guys. But I'll let you know a secret. Celebrating your 50th birthday is a huge thing in the decimal community. Maybe you didn't know that, but we all work with it. I mean, if you look at the primes, it's just 2, 5, and then 5 again. It's nothing peculiar. I mean, 48 is much more interesting. So I don't know why, but I promised to be there, so that's why I included it. So we're based in Silicon Valley, California, and this talk today is from Java 1. I had it a few weeks ago. First I'm going to talk a little bit about microservices. Now presumably you know a little bit about microservices, and the time I have is shorter now than in Java 1, so I'm going to kind of fast forward here. But microservices can bring together the best from different areas. And of course, you are likely to use one of these best practices. When people see this for the first time, they think that this might be a kind of marketing hype. But then they have a progressive adaptation of the concept. So after a while, they think that maybe it sounds very familiar, or it's just rebranding of stuff we already do. And so they accept it more and more. And in the end, maybe they can just do it with just a few changes. So it's about simple component-based design. So we would like to decompose your monolith in smaller parts. And you have asynchronous messaging between those parts. And you can automate the way of you having new microservices, adding new instances, for example. So if you have too much load, or if you want to increase your redundancy, you can do that automatically. One thing that is very important in this aspect is that you have private data sets. So if you have one microservice, that microservice kind of owns its own data, and other microservices own their data. So you're not really allowed to go in and clap around with other microservices' data. It's private to them. And we will see how that will influence the solution I'm going to talk about today. You have transparent messaging, and the idea is that teams can continue to develop the microservices pretty much individually. So I'm going to talk about a solution where we have everything in the JVM. And before I do that, I want to position where we are, what kind of problem we're trying to solve. We are not going to solve a problem when we have hundreds of terabytes or thousands of terabytes in memory. That's not going to work today, but it might work in a few years. Rather, we focus on this area with very low latency. So we have microseconds latency here, or milliseconds. And maybe smaller data sets from gigabytes to maybe up to 40 terabytes is the biggest we ever did. So that's a lot. But maybe, I would say, maybe up to 10 terabytes, reasonably. And you can have low latency in the microseconds for that amount of data. So if you're looking at much bigger data sets, this solution is not for you. But if you're looking at smaller data sets, like a few terabytes and less, this might be interesting. Okay, so it looks like this. We have a lot of data, terabytes there. We have a solution, and on top of it, we run microservices. And the solution is basically comprises 4 parts. One part is synchronization. How do we synchronize SQL data into the NYJavaSIG memory store? 2 is a KeyValue Store, which is actually something like the table itself. It contains all the entries in a table and a key for it. And of course that's good if you know the key, but if you don't know the key, you need to be able to search for data in that data set. So therefore we have something called column key stores. So basically you have one column key stores for each column. And this makes your data searchable. And then there is an API, which is interesting because it relies on Java 8 streams. I will tell you more about that later on. So it will look like standard Java 8 streams, but still gives a very good performance. And you can deploy a number of microservices on top here. So, go first to synchronization. It really scoops up data from the database and pushes it into memory. And there are two aspects of this. First, you have to do it initially, because when you start your application, you need to have some kind of data there from the beginning. And then, over time, how do you keep your memory representation current? So you can do it periodically, or you can do it reactively. Periodically, you fetch data regularly, and reactively, you react on what's happening in the database. So, for the periodical solution, you just remove down. So typically, you select star from some kind of table, and you put everything into memory. And everything is loaded, and between the reloads, your data remains the same. So if you restart, you just reload everything, and then there's a multi-versioning control thing here, so that if you are processing stuff from an older version, you can continue to do that while the new one is loading. So you can have several versions at the same time. Excuse me. Do we have water there? Yeah, it's here. Okay, and then we have a reactive way where you capture the data changes in the database itself, and you push it into memory, and you group all the events in transactions, so memory will still reflect a valid view of your data. It will still be consistent. And as data changes, data is consumed by the memory updater, and if you restart, you only have to replay the missed events. So I think is a good property. Just give me a second. Okay, so the difference between a periodic and reactive is typically the max data age. So typically, for a down period, you can reload maybe once an hour, once a day or something. Whereas with reactive model, it's about milliseconds, maybe 10 milliseconds delay of your data. And another interesting aspect is if your update goes down, then you just have to replay. So it might be like 10% of the downtime that you need to recapture where you were. So if you go down 10 minutes, it just takes 1 minute to go back again, even if you have very big data sets. And I think these two algorithms have their benefits, but they're very much better than when you expire things with poll, because then you have inconsistent data, you have no control of when you reload stuff. And when you miss the catch, or if you miss data that's been expired, you need to collect them from the database. And that is kind of 10,000 times slower than getting it from memory. Okay, so we can detect changes in the database, buffer the changes, we can replay the changes later on, we preserve the order in which they were inserted in the database or changed, preserve transactions, and see that it was persisted, like if you had sequences or auto-increment columns or whatever, or triggers. And you can detect changes from any source, like if you have scripts or third-party application, whatever you have. So how can we do this? Yeah, for the reload, it's very easy. We just reload. But we can also do transaction log harvesting. So we can harvest the transaction log in the database, and we can see what's changing, and then we can feed it into the memory grid. And you can also use something called event sourcing and CQRS, which is becoming more and more popular within the microservice community right now. This is like if you have a salary increase of 1K, instead of updating a database row with like replace salary with salary plus 1,000, you instead insert something that says that the salary increased by 1,000. And then you have an aggregated kind of functional fold of every event that's ever occurred. Okay, now we go to the KeyValue Store. And the KeyValue Store is working off heap, and it works on memory map files. And that opens up a way of having very big JVMs. So you can have them like 40 times bigger than your available RAM JVM itself. And you can have like tens of terabytes of data. And by mapping it to a file, it's automatically persisted. And when you have multiple instances of a service, you can just start and map that file. So once you start, you have that memory available right away. So how much data can we have? Well, we started a long time ago, we only had 32 bits. Now we can only have 2 to 3 gigs. We got 64-bit systems, and by using compressed OOPs, we got 3 extra bits, so we can have 35 bits, but still use 32 bits addressing. And with Java 8, we got another feature that allowed us to have an arbitrary byte alignment, like 16, for example. 16 is particularly good because it's kind of a trade-off between the holes you make when you align your objects and the scale of shifting. So you get like 4 bits instead. So you can have up to 64 gigs with just 32 bits index or object memory references. And that's good because your cache and everything will work much better if you only use 32 bits compared to 64 bits. If we go to the next level, let's use pure 64 bits, and that comes with a cost. And of course, you're all aware of the bigger heap you have, the more of a concern the garbage collector will be. So after a while, you should prefer to use the G1 collector, but still, if you go to 20 to 25, maybe if you are very careful, you can go to 64 or something, but you will run into problems. Which you don't have if you have an off-heap store. Next step is the NYJavaSIG. Well, you think you have a CPU, which is like 16 cores or something, but actually you have a collection of computers inside your chip. So usually it's like 4 computers with high-speed buses. And the problem is when you have a JVM that spans over NUMA borders and you use garbage collect, then the performance will go out of the window. That's important to understand. Next limit is virtual address page. This is 48 bits mostly. And then with memory map files, you can go even further. And if you have library support, you can go over 50 bits. So you can have like petabytes again. So you're really not limited by physics here. It's more imagination stuff. So how does this work then? You have a user space with your JVM, and you have your memory model here, and you have map buffers to physical memory, and then you have a file system which is mapped to the file over here. And of course, if you want performance, you want more RAM. If you can accept page faults, you can have less RAM. It's a trade-off. But they've been working with this in the operating system for 30 years, and they're very good at it. And this is if you have really, really big data sets in your JVM. You must have some kind of replication, because if the node goes down, it will take 2 weeks to reload. So if you have really big JVMs, you must have some kind of redundancy. Okay, let's go to the current Keystore. It's basically like a database index, which makes your data searchable. And it can produce data lazily, meaning that it can produce elements very quickly as you consume them. You don't have to populate a list, for example, with everything. You can just consume it as you go along. And they can also be mapped to memory map fairly, exactly in the same way as a KeyValue Store. So it's a kind of concurrent navigable map, but it has some additional features. You can have null values, and you can have several values for one key. Thus, it's kind of a multi-map. You can serialize data off heap, and it can be mapped onto files, just as key map. You can compress its key. So if you have, like typically in a database, you have a sequence or an auto-increment field, you will get 1, 2, 3, 4, 5. So the KeyValue Store is able to store that very efficiently. It also contains a bidirectional skip dictionary. So if you, for example, want to find everything in name order but skip the first 100 million items, you don't have to skip 100 million items, but you can just jump directly to that spot. And it remains performant for billions or trillions of entry. Maybe if you go home and try your Java collections and add 1 million entries, and then you do a stream over that, you will notice that it will drop off significantly, because the standard Java collections are good in the Goldilocks field, kind of. They're good for fairly big amounts, but not very big. So we have to rewrite everything around that. It supports transactions, and uses exactly the same mapping mechanism as the KeyValue Store. So for example, if you want to add a microservice here, you just add it here in user space. And it will use the same physical memory and the same file mapping here. So this is the reason why it's so quick to just start a new microservice. So what can we do with it? We have a lot of operation, and the order one operations are these. Are you aware of the order notion, everybody here? Okay, the order says that how long time does it take compared to how much data I have. So if I have 1 million and I increase it to 2 million, order one means that it will take always the same constant time. It doesn't matter how many objects I will insert, it will take the same amount of time. Is null, is not null, and is in a set or not in a set. And it will also keep a view of the data sorted in both directions. So this kind of operation will complete in constant time. Then we have another group that will complete in order log n times, which is basically the same as order 1 time. I will show this later. So it will be a small increase of time as data group, but not that big. So then we have all the comparison operator, like less than, bigger or equal. And between, this is actually a composition of 2 of these guys up here. And start strip. And there are also some which is really order n, kind of, if you want to match a regular expression, for example, that's more tricky to do. So just a recap of big O's from computer science. The 2 down here are order 1 and order log n. And that form their own group. And then the yellow line is order n. And the blue is order n log n, which is typical sort behavior. So you can see that, well, being here is very good, being here is not so good. Okay, so let's take an example. If I have a predicate that looks like this, user age greater than 42. How is that handled? Well, obviously, it has something to do with the user. So we can look at the KeyValue Store for user, which is there. And there is a collection of column keystores. And in particular, there is a store for the column age. So the user age is this column store here. And I will just provide this predicate greater than 42 here. And that column key is able to produce keys that matches this predicate very effectively in constant time, basically, or long time. And then we just map those keys to the KeyValue Store, and then we get the entries like this. This is kind of a pipeline. Looks like this. So we have a predicate. The KeyValue Store will produce a set of keys, and that key will be translated to the KeyValue Store and produce values. And the column keystore can also work in parallel. So it's able to can produce a parallel stream of keys, which can be translated in parallel in the KeyValue Store too. And you can actually plug in your own parallel strategy here, because Java has a default strategy for an unknown size, and that strategy stipulates that you should put 1024 on the first thread, 2048 on the next thread, and then 3000, then 4000. And that's good for also in the Goldilocks zone, but it's not good if you have something that's very compute intensive, because then everything will be on the first thread, and then you don't have any parallelism. That's why this is important. Okay, now we come to the API, and the API is actually open source. So you can go to GitHub and to Speedment and download this, and you can try the API on a database, not an in-memory store, but on a database. And it looks like this. Okay, you first go there and you connect to a database. It will generate everything you need, like from POJOs and project setup and everything. So it reduces development time, improves the application quality, and reduces maintenance for your application. You just press this button, generate up here, and you get everything Java code, and you can review what it is. And it uses standard Java 8 streams for querying. And you can also modify the code if you want. So this is how it looks like. You have user stream, filter age greater than 42, and for example, for each, do some kind of operation here. This is how it looks like. So it's pure Java 8 standard. And there's also a REST API, which is basically the same, but only mention the filter here, like this. So, how does it work? Well, from the beginning, potentially you have all the values. You have the KeyValue Store of all the values, and you want to iterate on all the values and evaluate this predicate, and then you do something with it. But of course, that's very inefficient because you have 1 billion entries here. You don't want to evaluate this predicate against 1 billion entries, of course, because that would be very, very inefficient. So what we do is actually, when we execute the terminating operation, the stream itself will inspect its own pipeline, and it will realize that, wow, I got already a key column store for this age greater than. So if I replace the source using this column store instead and insert this KeyValue Store get, I will produce a pipeline that's equivalent from a functional point of view, but it's much more effective. So if we look like this, we will use the KeyValue Store, and then we'll go through the mapper, and we'll do stuff. And this is a very efficient solution, because if you only iterate other those expressed by the predicate directly. And I think that is a very important aspect of this solution. So then you can build up more complicated streams, like I want to filter out all older than 42, skip the first 10, leave it to 10, and then sort them, and then do some kind of operator, for example. Or you can use parallels like this. I have a stream which is parallel, I do the same filter, I do a flat map, which is basically a join. So I find all the logins for those users, and then I do something with it. Expensive operation like email them or do something else, aggregate all that data in some sense. So this brings me to the demo. How does it look like? In the first demo, I have 300,000 users, which is not very much, but I only have a laptop, and you don't have time to sit and wait because we load everything. We have enough heap data store and a key value map, and the test is find all users with ID 42, count them, add the count to a sum, and then do this 1 million times. And there's first the JVM warm-up, and then the benchmark, and of course the sum will be 1 million because there is only one user with ID 42, so this is just a test. And just to give you guys an idea, a normal database will be able to do like 2,000 transactions per second on that kind of laptop. So we will see how efficient the solution is. Can you see this? Okay. So let me show the code. It refuses to answer my clicks. Okay, luckily we have this one. Kind of refuses to go. There we are. So let me pull this out so you can see it. Oh, this is an analog display, so it's, you know, I'm used to HD, so we need to make it much smaller.
VGA stuff.
Yeah. You don't see VGA so much these days. I have to actually go and buy this adapter. Okay. Let's see what's happening. Let's make this smaller. Let's make this bigger. So we see that we have the size is 300,000, and we do 1 million iterations. And then there is a test. We print out some headers, and then we do 2 rounds, one warm-up and one benchmark. We have something called a stopwatch here, which is just meant to time how long time it takes, and then we do the actual sum. So this is the interesting function. then we stop the stopwatch, and if it's a benchmark, we print the result, and then we just quit. So let's see how this sum function looks. We start off with the sum equals 0, and then we do 1 million iterations. And they're very interesting stuff. We add to the sum user stream dot filter uses ID equals 42, and then we count that. So this is the stream API. So let's run this and see what happens. So let's make this one a bit bigger. So now there's sorting loading. Now it's starting. Wow, this is small. Okay, success, that's good. Let's see if I can see. Okay, it's more than 500,000 transactions per second, so it's very quick. So I think that's good. You can also see an interesting thing here is the latency. The total wall clock time here was 1.2 seconds, but remember that we did 1 million operations. So actually the latency is 1.4 microsecond, because we're only using one thread right now. So I think this is really low latency. Okay, let's go back to the next demo, which is a mixed predicate. We add some interesting predicate with equals or sets.
Sorry, I didn't get that.
Okay. I'm sorry too. So we have a list here with the predicates we want to evaluate. Users ID equals 42, users ID greater or equal to 42 in the set or between. And then we just modify our sum, so it takes a predicate as a parameter, and then we apply that predicate in the filter, and we just find the first one, and if there was one found, we add 1, and otherwise we add 0. Now the reason I'm doing this is not cheating, because I only want to find the first, because otherwise it's not really comparing them, because greater than 42, and almost everybody is greater than 42, so we cannot compare them. But this is just to find the first one. Of course, if you want to process 1 million, you have to process 1 million, but this is just a finding function. Okay, so let's run that too. And iterations, yeah, let's... Also, we have 1 million in size now, so it's more than 3 times more data than before. So that's good to be able to test the asymptotic behavior. So it will take a little bit longer time right now to load this because it's more. And now we can see it's sorting here, and everything is in parallel because the column stores are independent from each other, so they can be managed in separate threads. And now it's ready, and now we're running. And because we are using 4 predicates, it takes longer time for the warm-up.
The 4 predicates you use as different keys, right?
Sorry?
You have different keys with the 4 predicates.
We can take that question later. Sure. Okay. So now we can see here we have the 4 predicates like this, and they all count in the same, which is you do. And now we can see the transaction time here. So they're still about the same. As you can see, the comparison is a bit slower, but it's not a big difference. So then you will see that this log n is about the same as order 1. So when there is a last demo I would love to share with you. How is it with time? How are we?
You get that 10 minutes.
10 minutes, okay. So let's see, the last one is for parallelism. We go back to 300,000, but we use 3 threads instead. So let's see here. I'm going to guide you guys. This is kind of, I work with completable futures here. I'm going to compose all the tests in one, and then I just apply them here and add the result of them, so they will work in parallel. So let's start it here. 5. So we started, and now it's warm up. kind of a cliffhanger. Will it work or will it crash? Everything for the excitement. Actually, it's not doing anything. It's just for the tension. You know? Yeah. Well, something happened. Yeah. So now we're in the millions of transactions because of the level of parallelism. Let's wait the second one, last one, before it will. There we are. Wow. So we're in the millions of transactions. So I think this is quite good. And this is just a laptop, and I haven't really plugged in my power cord, so it's in save mode, power save mode. So with the server, obviously, you will get much better performance, like if you have 32 threads and have much more efficient CPUs than I have on my laptop. So that was the demo session. So just a small recap. If you compare latencies with the speed of light, because milliseconds and nanoseconds is kind of an abstract way for us humans. We also used to work in this middle world. So I used to take this analogy of using the speed of light and illustrating 1 second. If you take a database query that is 1 second, now arguably the database query can be much quicker than 1 second, but it can take 1 second. And this is about the time it takes for the light to go from the Earth to the moon. But if you have data from your level 1 cache, it's just 4 inches. So that will give you an idea what we're talking about, what is in memory. Because there are a lot of databases that are in memory, but they're not on the same node. So it doesn't matter how quick they are. If they will complete in 0 nanoseconds, it doesn't matter because we still have their hops in the network. So that's one thing. And another, so conclusion there, don't put your data on the moon. Keep it in your in JVM. And another thing that I can reveal for you, except for the decimal community, is that we have reached an epic threshold for mankind actually in 2016. And that is 1 gigabyte of RAM is cheaper than a coffee on Starbucks.
Starbucks.
Starbucks, yeah. So conclusion, quit drinking coffee and buy more RAM for your applications. You get tremendous performance from that. So this is the solution. You have databases, you can have an in-memory solution like this one, and you can have your microservices on top, very high performance. The solution is based on navigable maps to be able to search your data. And the views of the maps are available to any JVM that has access to the memory map files. Microservice JVM can be started very rapidly. And the access to the maps will be gained in millisecond time. So if you restart, you're up immediately. And you can share them between the microservice JVM, and you can add new or remove old one and restart them very rapidly. Instantly, I would say. So, if you only remember the one thing, I didn't say that I can solve all the big data problems in the world. I only said that I can solve low latency for a moderate set of data. Because people tend to criticize themselves. This will not work with 600 trillion exabytes, and I agree, it will not. So, that's my presentation. Thank you very much. So, yeah, you had a question there for me? Yeah?
Before when you were showing the filters, you basically only showed just one column.
Yeah.
One across multiple columns.
Yeah. Yeah, question is, I only showed one column, and the thing is that it will inspect how many filters I have, and it will select the best data source it can do with that set of filters I have. So if I have 5 filters, and maybe I have one filter that is very broad, and another one that is very narrow, it will pick the narrow one. And it will also look at what kind of predicates are there. Is there an identity or equality predicate? It's more likely that I can execute that rapidly than a regular expression, for example. So, and you can also control which one is being used. So in another variant, the first one is used. So if you want to be able to control as a programmer, you can use the first one as the preferred predicate. Yes, next question down there.
Does it support multiple table joins, like data source joins?
Yeah, question is, does it support multiple joins? Yes, it does. There is one thing you can do with a stream, and that is an operation called flat map. So you can take something, an entity, and then you can flat map that onto another memory map solution. And that flat map will actually flatten out all the streams generated by the other and replace that in the stream. So that is effectively a join. And you can do that in chains, so you can have like any number of joins, and everything will be in memory.
And the performance comes up comparable?
Yeah, actually those flat maps will have the same property as the initial stream has. So it will also be able to use those column stores. So they will be as efficient as the first predicate. So it's very efficient, yes. Yes, question there?
How in the world is sort order 1?
Yeah, that's a good question. How is it order 1? The answer is that it maintains a sorted view all the time. It doesn't do sort. So it has already a maintained view of if you want to sort it, it's already sorted.
And amortize-wise, is it taking time to keep things in sorted order?
Yeah, it takes time when you build up the column stores from the beginning. So it's pre-sorted. So that's why it can be an order 1 operation.
So insertion of a new value must take more time.
Insertion of value will take more time. But insertion of a value is also order log n. So it's a very low cost for it. But yes, it will take slightly more time.